Hey everyone, Dr. Kem here, and I am absolutely thrilled to be your guide for today's explainer. We're diving into a topic that sits right at the perfect intersection of practical physics, renewable energy, and, quite frankly, the future of our planet. We're talking about solar cell efficiency measurement. You know, we constantly hear these exciting news drops about new world record solar cell efficiencies, and it makes sense. These incredibly vital devices use the photovoltaic effect to convert sunlight directly into electrical energy, and we literally rely on them everywhere now. I mean, they power our homes, massive industrial farms, satellites orbiting the Earth, down to the portable electronics in our backpacks. But have you ever stopped and wondered about the rigorous, highly precise laboratory science required to actually prove those world record numbers? Well, today we are going to look exactly at how scientists test these cells and the truly incredible links they go to just to get the math perfectly right. So this brings us to the central mystery of our explainer. At its most fundamental level, measuring efficiency sounds just like a straightforward student physics experiment, right? You essentially just need a light source, a multimeter, a variable resistor, and a ruler. Energy conversion efficiency is basically just the electrical power output generated by the solar cell divided by the incident solar power hitting its surface, all multiplied by 100. Easy. But when billions of dollars in renewable energy investments depend on a tiny fraction of a percent difference in performance, how do primary photovoltaic metrology labs take that basic physical principle and definitively prove a cell's efficiency without a shadow of a doubt? Okay, let's dive right into this. Here's our roadmap for today. We'll start with the foundational solar cell IV curve, then establish our standard reporting conditions. From there, we'll look at how we simulate sunlight indoors, tackle the really tricky spectral mismatch problem, break down the precision measurement techniques used to fix those errors, and finally, look at how testing emerging solar tech is completely changing the game.
Part 1. The solar cell IV curve, the fundamental visual tool. To understand efficiency, we absolutely have to understand the backbone of solar characterization.
It's amazing how much crucial information is packed into this single shape. What we're looking at is an electrical current versus voltage, or IV curve. When we connect our solar cell to a variable load and measure it under a constant light source, we get this exact profile. Up on the y-axis, we have the short circuit current, or ISC. That's your maximum current when the voltage is 0. Then, way out on the x-axis, we have the open circuit voltage, VOC, the max voltage when no current is flowing. But the real magic? That happens right at the knee of the curve. That specific point is Pmax, the maximum power point. Because electrical power output equals voltage multiplied by current, this one spot is where the solar cell is operating at its absolute highest efficiency.
Now, while we've got this curve in front of us, we really have to talk about fill factor. Imagine a perfectly flawlessly ideal solar cell. Its curve wouldn't be curved at all. It would form a sharp, right-angled rectangle. But, real-world physics intervenes. The fill factor is a critical metric that reveals the internal health of the cell. It's essentially a visual indication of internal losses, like series and shunt resistance. Basically, the more the curve sags and deviates from that perfect rectangle, the lower the fill factor, and ultimately, the lower the overall efficiency of our device.
Moving on to part 2, standard reporting conditions. This is all about leveling the playing field. We know what to look for on our graph, but here's the next massive hurdle. We simply cannot accurately compare a solar cell tested outside on a cloudy Tuesday in London with one tested on a scorching Friday in Arizona. The weather, the angle of incidence, dust accumulation, it all constantly changes. So laboratories worldwide use standard reporting conditions, or SRC. First, you need a total light irradiance of exactly 1,000 watts per square meter. Second, the light has to perfectly match the AM 1.5G standard reference spectrum, which mimics sunlight at mid-latitudes on Earth. And third, and this is super important, the physical device itself has to be kept at exactly 25 degrees Celsius, because a hotter solar cell actually drops in voltage and loses efficiency. If you ever buy a commercial solar panel and it gives you a specific wattage rating, it was determined under these highly controlled conditions. Section 3. Simulating sunlight indoors. Creating a fake sun. Because, let's be real, getting perfectly consistent 25-degree weather with exactly 1,000 watts of perfect sunlight outdoors is practically impossible. So, labs have a very logical solution. We just bring the sun inside. We use incredibly sophisticated apparatuses called solar simulators. These machines use really powerful xenon flash lamps to just blast the test cell with light. But look closely at this graph because it brilliantly illustrates a massive hidden challenge. The solid black line is the light spectrum created by our simulator. Notice how it's full of dramatic, jagged spikes? Now, the red dashed line is the smooth, actual AM 1.5G sunlight we actually want. As you can clearly see, our fake indoor sun is definitely not a perfect match for the real thing. Which brings us perfectly to Section 4, the spectral mismatch problem, the flaw in the fake sun.
Because our indoor sun is flawed, we run into some serious optical errors. Different solar cell materials like silicon, cadmium telluride, or organic compounds absorb different colors of light. If our simulator happens to output too much blue light, a blue-absorbing cell is going to look artificially way more efficient than it really is in nature. To solve this, scientists use a calibrated reference cell to monitor the simulator's light. But if that reference cell is made of silicon and your test cell is made of something else, they're going to see that flawed light entirely differently. It's kind of like listening to a live cover song versus the original studio track. Some notes just hit differently. Labs quantify this divergence using a spectral mismatch factor, or M. Check out the data here for testing an organic PV cell using a standard silicon reference cell. It yields an M factor of 1.089. That means there's an almost 9% error right out of the gate, strictly from the lighting mismatch.
Section 5, precision measurement techniques. Correcting those errors. Because an error of 9% is totally unacceptable when we're verifying global world records. So scientists deploy some strict mathematical procedures to achieve those crazy sub 1% measurement uncertainties. Step 1, they adjust the simulator using a perfectly calibrated reference cell. Step 2, they calculate that spectral mismatch factor, M, by integrating the spectral response of the test cell, the reference cell, and the specific spectrum of the simulator lamp itself. And finally, step 3, they apply M to mathematically correct every single raw data point on that IV curve. But optical errors aren't our only headache. The very connecting wires we use to test the cell can actually ruin the measurement. Every wire has its own resistance. Pushing high current through a simple 2-wire setup causes a voltage drop, completely skewing our efficiency calculation. So we use a 4-wire or Kelvin connection. We separate the source leads that carry the heavy current entirely from the sense leads that measure the voltage. By separating them, we read the true voltage directly across the device. This ingenious principle is exactly identical to the 4-point probe equation right here, which is a vital tool for calculating true sheet resistivity. Now let's look at how all this painstaking work builds into our final result. The difference is literally night and day. The black line is the raw, uncorrected measurement. It's noisy from short-term lamp fluctuations and entirely skewed by spectral mismatch. But the red line? That is our final, highly precise, corrected curve scaled perfectly to standard reporting conditions. That beautiful red curve right there is the absolute, undisputed truth of the solar cell's performance. Finally, Section 6, Testing Emerging Solar Tech, the perovskite wildcard. Just when metrologists perfected this exact science for traditional silicon panels, material chemists completely flipped the script. Enter perovskite solar cells, or PSCs. These cutting-edge materials are rocketing past 26% efficiency, but they have a very strange property. They exhibit hysteresis. Because ions actually move around inside the material during operation, the cell has a kind of internal memory effect. If you measure the voltage sweeping from low to high, you get one IV curve. But if you measure it from high to low, you get a completely different curve. How fast you run the test and whether the cell was left in the dark or the light beforehand completely distorts that traditional IV curve we just mastered. To accurately test perovskites, the old static methods just aren't enough anymore. Scientists are practically writing a brand new textbook for this. They're having to apply incredibly dynamic techniques, like sweeping the voltage in continuous sinusoidal waves rather than straight linear lines. They're deploying small signal impedance spectroscopy, applying tiny AC signals over DC biases across all sorts of different frequencies. They even use advanced Fourier transforms just to map out whether the cell is acting more like a capacitor or an inductor. They have to decode this insanely complex nonlinear performance just to figure out what the true fundamental efficiency actually is. Which leaves us with this final thought. You might look at all these experimental precautions, simulated suns, 4-wire connections, and mismatch corrections and think, wow, that's just overly obsessive lab work. But accurate measurement isn't just pedantic laboratory science. When a utility company buys 1 million solar panels for a new massive solar farm, a 1% error in efficiency measurement translates to millions and millions of dollars in lost power and wasted resources. Our ability to build a sustainable, renewable energy future relies entirely on our ability to precisely, unequivocally measure it today.
I'm Dr. Kem, and I hope this explainer has illuminated the brilliant scientific principles behind solar energy conversion. Keep asking questions and keep exploring.